Okay, so now recording. Okay, so we talked about cofactor expansions of a matrix. So we can have a cofactor expansion along a row or along a column. And so each cofactor expansion gives the same value. And so if you go along any row or any column, you get the same number. And the determinant of a matrix is determined by these cofactor expansions. Okay, so here at the bottom, I gave the definition of a cofactor expansion. So what I'm going to do is I'm going to bring this over to lesson 15. So this was last class. We ended with this definition of a determinant in terms of cofactor expansions. And so this class, I want to start by giving an example, another example. I gave one example last class, another example of finding the determinant of a matrix. Okay, so we're going to use this definition to find the determinant. So according to the definition, we can take a cofactor expansion along any row or any column of a matrix, and it will give us the determinant. So this vertical line, when you draw a vertical line on both sides, that's denoting the fact that you're finding the determinant of that matrix. So we're finding the determinant here of this matrix. And so I'm going to take this determinant along the first row. Okay, so notice that you want to always make your life as easy as possible where you can. So if you can choose any row or any column, notice that there's a 0 in the first row. And so zeros help. Zeros make computations easier. So I chose row 1 because it has a 0. I could have also chosen column 3 because the 0 is also in column 3. But I chose row 1. So in order to find this determinant, you have this formula here, right, for rows and columns. And so technically you would be applying this formula. Now it's much easier to do the calculation without thinking about the formula. So what you want to do is for each element of the row, for instance, you have this entry 3 here, right? You're going to have a 3, and then it's going to be times the corresponding determinant of a corresponding 2 by 2 matrix. Then you're going to subtract 1. It's going to be times another corresponding matrix. And then you're going to add 0 times another corresponding matrix. Okay, notice that 3, 1, and 0 are the entries in the first row, and we're alternating the sign of these entries starting with positive. So it's positive 3, then minus 1, then plus 0. The minus sign doesn't mean negative. So if I was doing the second row, it would be negative 2, then negative 4, which is plus 4, and then plus 3. Okay, so it's not positive, negative, positive. It's the exact value there, the negative of this number, and then the same as that. It would be same, negative 4, which is 4, and 3 for the second one. Okay, so you have these values. And then for each of these corresponding entries, whether plus or minus them, depending on the checkerboard pattern, you take the entry and you remove the row and column that entry is in the matrix. So if you remove the row and column that this number 3 is in, this entry 3 is in, you're left with a 2 by 2 matrix, negative 4, 3, 4, negative 2, because I removed the row and column in which this entry was in, and you're left with the rest of it, and you take the determinant of the rest of it. So if you have an n by n matrix and you choose any entry, and you remove the row and column in the matrix that entry is in, that results in an n by 1 times n by 1 matrix.
Professor, I have a question.
Sure.
Yeah. So I'm still confused. Why do you choose -1 and +0?
Because that goes back to finding the cofactors of each entry. So, so let's go back to lesson 14. So, okay, so the cofactor. So we had entries of our matrix, right? The original entries. For each entry, we found the minor of that entry. Okay, So each entry of your matrix has what's called the minor of that entry, and we denote it by capital M sub whatever the indices. So the minor entry of A11 is capital M sub 11. It's the determinant of the submatrix, right, that we have already. Now, in addition to a minor of the entry, we also have the cofactor of an entry of a matrix. So the cofactor of A11 is -1 to a certain power of M11. Okay, where M11 is your minor. Now you're taking -1 and you're raising it to the sum of the numbers down here. So it's -1 to the 1 plus 1 times M sub 11. And so all that's happening is that the cofactors, here we have a matrix of minors, where for each entry of the matrix, we have a corresponding minor for that entry. The cofactors of these entries are just plus or minus the minors of those entries. So see how the cofactors corresponding to the entries are the same as the minors on these points, right? Here in in blue, these cofactors are the same as the minors. Okay, and then everywhere else where it's red, it's the negative of the minor. Do you see that?
Yes.
Okay, so where it's blue, the cofactor of an entry is the same as the minor of the entry. Where it's red, it's the negative of the minor. Now, what you have is that if you take the determinant of a matrix, right? If you go along any row or any column, if you take each entry in that row or column and multiply it by its corresponding cofactor, the sums of those products always equals the determinant of your matrix. And so what you need to do is to find the cofactors of each entry in your row or column you choose, take each entry in the row or column, multiply it by its corresponding cofactor, add the products, and what you get is the determinant, regardless of which row or which column you choose. And so the cofactor, the pattern of plus or minuses of the cofactors is this checkerboard pattern, that the top left thing, the cofactor is the same, and then it alternates as you go up, right, up, down, left, right. See that? So all we want to do is we want to find the determinant. The minor is the determinant of the submatrix. The minors are the determinants of the submatrices, and then the cofactors are plus or minus those determinants, depending on where you are in the matrix. So this is the same as the determinant of the submatrix. This is the negative of the determinant of the submatrix. This is the same as the determinant of the submatrix. So in our example,
Professor,
yeah,
just a quick question. What if there 16 is negative? So what do we put for the other cofactor value?
you mean if the term is negative?
No, if you go back to other.
Okay, sure.
Yeah, right here. What if 16 is negative? And do we do like positive 10 or no?
Wait, you mean here?
Yeah, so let's say on the upper line is 16, 10, 3, 24. They are all positive, right? Positive values. So what if 16 is a negative value?
Oh, but then it would stay -16. It's just
negative. Then it would been positive 10 or no?
so if the minor up here was a -10, then this would be a +10. So
it changes the sign.
Yeah, it's not about positive or negative. It's about either the same or opposite to the minor entry.
Oh yeah, I got it. All right,
Makes sense?
thank you though.
You're welcome.
I got it.
So what's happening here is I'm choosing them all to be positive, so it's you can see the pattern between the alternating or the same. But the real rule is not plus or positive or negative. The real rule is same or opposite in sign to the minor entries. Okay, good. Okay, so you get it. Okay, so what's happening here is that for each entry, you then multiply it by either the determinant of the submatrix or the negative of the determinant of the submatrix. And so a faster way to do it is just take a row or column where the top left entry is the same, and then alternate between same and opposite in sign, and then multiply each one by a determinant of the submatrix. You get by removing the row and column in which that entry is in the matrix. So this entry here, 3, if you remove the row and column it's in, you're left with this as its submatrix, and you take the determinant of it. And so it's 3, that entry, times the determinant of that submatrix. The next entry, you're taking the negative. So it's the negative of the entry times the determinant of the submatrix. Now, the 1 is there, so you remove the row and column that 1 is in. You're left with -2, 3, 5, -2. So now, when you remove the row and column that 1 is in, you're left with -2, 3, 5, -2. Keep the order the same. And then lastly, you have the 0 matrix. Now, you know 0 times anything is 0, so you almost don't even have to do this step. But I want for completeness in the explanation, I'm going to add it. So this is in the first row and third column. So if you remove those rows and columns, you get -2, -4, 5, 4. See that? So I remove the row and column which that 0 is in. And so now I'm left with that submatrix, and I take the determinant of it, and I multiply it by the positive of that entry, which is 0. As now you take the sum of those products, you get the value of the determinant of that 3 by 3 matrix. But the point of this was to reduce our problem of finding the determinants of a 3 by 3 matrix by finding the determinants of 2 by 2 matrices. Okay? Because our original formula is the determinant of a 2 by 2 matrix. And so we can always use this process to make the sizes of our matrices that we're finding determinants of smaller. So if we had a 5 by 5, we could express it in terms of the determinants of 4 by 4 matrices. And then each determinant of a 4 by 4 matrix, we could determine it as an expression of determinants of 3 by 3 matrices. And then each of those determinants of 3 by 3 matrices, we could express each of them as expressions using only determinants of 2 by 2 matrices. And so it's a lot of work. But eventually, you can just use the formula we had at the beginning, that the determinant of a 2 by 2 matrix, whose entries are A, B, C, and D, that the determinant of that matrix is equal to AD minus BC. Okay, and so now we can use that formula to get this answer. We can calculate each of the determinants of these 2 by 2 matrices, plug them in, and then find the final expression. So this is equal to 3 times. So the determinant of that matrix is 8 minus 12. This is -1 times 4 minus 15. This is plus 0 times -8 minus -20. Okay, so I kept the logic of my step the same. So I did instead of just writing the determinant, I wrote it as the difference of 2 products. So I wrote AD minus BC for each one. Okay, so this is 8 minus 12 for this determinant. This is 4 minus 15 for this determinant. And this is -8 minus -20 for that determinant. Okay, so in between steps, so you can follow what I'm doing. This is 3 times -4. This is -1 times -11. And this is plus 0 times 12. -8 minus -20 is -8 plus 20, which is 12. Okay, and so now this is equal to, and so you can just finish these calculations, -12 plus 11 plus 0. And that's equal to -1. 3 times -4 is -12. -1 times -11 is plus 11. And 0 times anything, 0 times 12 is 0. And so you get -1. So we found the determinant of this 3 by 3 matrix is -1. Okay. Okay, so now that's an example of using the cofactor expansion along the first row of this matrix to find its determinant. So above, we found the determinant of that matrix by finding its cofactor expansion along its first row. Okay, the cofactor expansion along the first row is just this expression. This is called the cofactor expansion of that matrix along the first row.
I have a quick question.
Sure.
So did you choose the first row like for any particular reason because it says so, or is it any row could be chosen?
So two things I'll say. First, any row or column could be chosen, right?
Okay.
This definition here, it says that okay, so if A is an n by n matrix, then the number obtained by multiplying the entries in any row or any column, any row or column of A by the corresponding cofactors and adding the resulting products is called the determinant of A. And the sums themselves are called the cofactor expansions of A. So along any column J, this expression is the cofactor expansion along column J that's equal to the determinant. Along any row of A, this is the cofactor expansion along any particular row of I of that matrix, and all of them are equal to the same number of determinants of that matrix.
Okay. Thank you.
Another thing, though, you have a choice between any row or any column you want to choose. I chose the first row because it has a 0 in it, which means that when you add products, one of the products is 0 times something, which has to be 0.
Okay.
Make sense?
Okay.
So if you have a 3 by 3 matrix where there's a row with 2 zeros in it, you would want to choose that because then it would only be one product you'd have to worry about.
Okay. Thank you.
You're welcome. Okay. It's a little weird, but once you get the hang of it, it can be pretty easy. Okay, so let's do another example. Before you understand the theory or understand the definition or the formulas, the easiest thing is just be able to compute it. So here we're going to compute another determinant. So example 4 is find the determinant of the following matrix. So again, this is the notation for the determinant of a matrix. So you have 3, 1, 0. It's the same matrix. Oh. Okay. Oh. All right. Oh, I see what. Never mind. Okay. So I'm going to choose the cofactor expansion along the first column. Okay. Okay. So we're going to find the cofactor expansion along the first column. Okay. So we are finding the determinant of this matrix by finding the cofactor expansion along the first column, right? The cofactor expansion, of the matrix along the first column is equal to the determinant of that matrix. And so that's why we're finding it. And going back to the previous example, we find the determinant of this matrix by finding the cofactor expansion along the first row, right? And the cofactor expansion along the first row of the matrix is equal to the determinant of that matrix. So it's also equal to the determinant of the matrix. And so find the determinant of the matrix A. Okay, I'm calling it A. This matrix is called A. Okay. Okay, so we're going to find it along the first column, which is also its determinant. So again, you're going to take each entry in the first column, and you're going to, so first you're going to keep this the same as the first entry, then it's going to be minus the second entry, then it's going to be plus the third entry. Okay, so each one is being multiplied by a corresponding determinant of a submatrix, but the entries are going to be the same, right? So this entry here in blue is the same as this one. This entry, which I'm going to do in red, now we're going to take the negative of that term. And then this term, which is in blue again, we're going to take the same value as that term. Not its negative, just the same. Okay, and so for each one, when you get up to that term, you remove the row and column that that entry is in, and you take the determinant of the resulting submatrix. So this is -4, 3, 4, -2. That's the determinant of the submatrix for removing the row and column that that 3 is in. That 3 is in. Now, if you take the -2 and you remove the row and column it's in, you have the submatrix 1, 0, 4, -2, right? You take this -2, remove the row and column it's in, you have 1, 0, 4, -2. And then if you take this entry 5 and you remove the row and column it's in, you get 1, 0, -4, 3. Okay, so you have this 5 and you move the row and column it's in, the third row, first column, and you're left with that submatrix. So you take the determinants of those submatrices, you multiply them by these things, and then you get the cofactor expansion along the first column. So this is 3 times. Now something plus 2 times something else, plus 5 times something else. Okay, keep in mind that now they're all positive. It's only because it was a minus -2 here that became a +2, right? So alternating plus or minus does not mean that these terms again have to be plus and minus alternating. They could all be positive. It's just the same or opposite sign of the original terms of your matrix in that column or row. Okay, so in the parentheses are the determinants of each of these matrices here. So this determinant is 8 minus 12, according to the formula AD minus BC. Determinant of this matrix, the determinant of that matrix is -2 minus 0. And determinant of this matrix is 3 minus 0. Okay, so then this is equal to 3 times -4 plus 2 times -2 plus 5 times 3. Okay, now, so if you're following all these calculations, this is now -12 minus 4 plus 15. And when you add and subtract them, you get -1. So -12 minus 4 is -16. And then miraculously, plus 15 is -1. And that's the same value we got here. So taking the cofactor expansion on the first row gave us the same value as the cofactor expansion along the first column. And that's the number that represents the determinant of this matrix. And so our answer is the same, even though we chose the first column instead of the first row. Okay, and this definition says that. Okay, well, it says the conclusion that the determinant is the same as any cofactor expansion, is defined by any cofactor expansion. In last class, we showed how every I stated that every cofactor expansion of any row or any column gives you the same number. And so you see that in this example that it's happening. Okay, so now let's do another example. So in this example, we're going to talk about a smart way to find the determinant of a matrix. Okay, so there is some creativity sometimes in finding the determinant of a matrix. So we have our formulas, and we kind of have, in some sense, a formulaic way of doing it. But sometimes there are better choices for how to find a determinant, and sometimes there's worse ones, right? If you choose the wrong one, you could be sitting there for an hour doing it. Well, if you choose the right way to do it, you could do it in 30 seconds, right? So, so for instance, let's find a determinant of this 4x4 matrix, okay? Now, following our procedure, you have to think of the determinant of a 4x4 matrix in terms of determinants of 3x3 matrices. Then each of those 3x3 matrices, their determinants are determined by determinants of corresponding 2x2 matrices, and then you evaluate. So that would be a lot of work. So you want to look for shortcuts. So in this problem, there is a shortcut. Okay, so and so now you have 2, 0, 0, 1. So we want to find the determinant of this 4x4 matrix. And now we can do it using any row or any column, the cofactor expansion along any row or any column to get the same correct value. So what we want to do here is just find the cofactor expansion of this matrix along the second column. So if you find the cofactor expansion along the second column, then as you can see, there's 3 terms that are 0 in the second column. And so that means there's only one term which you have to actually compute something, right? Below, I'm just going to reminder of the checkerboard pattern. Okay, so we had a checkerboard pattern in which we determined the positive or negative sign, for the minor in order to get the cofactor of an entry. So here, let's look at the checkerboard pattern here. So right, you always start with the plus on the top left side, and then as you go up, right, down, up, down, left, right, the sign just changes. So now this is a minus, and this is a minus. This is a plus. This is a plus. This is a plus. These are minuses. These are pluses. Okay, diagonally doesn't change the sign. Moving up, down, left, or right changes the sign. So you have this checkerboard pattern of pluses and minuses. And so this is saying that you either use either the cofactor of an entry is the same as the minor of that entry, or it's the negative of the minor of that entry. The minor of an entry is the determinant of the submatrix. Okay, so here we're going to take the cofactor expansion along the second row. And so what I'm going to do is I'm going to denote this by green. Okay, so we're going along the second column, right? The top left entry of your matrix is plus, but because we're starting with the second column, that means that the first entry we're going to care about is actually the negative, because we're starting the pattern here. And so we're going to take the cofactor expansion along the second column. Okay, once you get used to this, it's not as hard as is in the beginning. You're going to take -0 times a corresponding determinant of the corresponding submatrix, which is a 3x3 matrix. Okay, because we're starting with a 4x4 matrix, these determinants are going to be 3x3 matrices. So you have a -0 there, but now this is a plus. This is now plus the entry there times the determinant of a corresponding submatrix. Then it's -0 times the determinant minus because of this minus sign here, right? We're going along this column. And so we're taking each of these entries. We're either keeping the sign the same if there's a plus, or we're taking the negative of that entry if it's a minus. And then we're multiplying by a determinant of a corresponding submatrix. And then here's a plus. And so it's going to be plus this entry. It's going to be the same as that entry. So it's going to be plus 0 times the determinant of the submatrix. Okay. So keep in mind, this is 0, right? This term is 0. This term is 0. And this term is 0 because it's 0 times the determinant. The determinant of a matrix, you get a number. And so any number times 0 is 0. And so this is actually this is equal to just one of those terms. Okay. But let me just talk about this one here. So this entry here, right? This entry here, you remove the column it's in. So you remove all the green entries. You also remove all the entries in the row that it sits in. So I'm removing all the entries also in the row that one sits in. So I'm removing all the green terms and the red terms. And now what's left is the submatrix that are not colored in. So this is 1, 0, -1. Then you skip the colored one. So next is 1. See the 1 here. Now after the 1 is a -2. You just kind of leap over it. You leap over the 1 now. Next is -2 and then a 1. You ignore it. It's as if they're not even there. And then this 2 is here. And then this is a 0 because you leap over the 0. And the next one's a 0 and then a 1. So that's the submatrix that you take the determinant of. Okay. Now all the other terms are 0. And so you don't even have to compute. You don't even have to find what these submatrices are because since it's 0 times it, it's fine. So now this is 1 times that determinant. And so it's just equal to the determinant of that 3x3 matrix. And so what we did by choosing the correct row or column is that we reduced the problem of finding determinants of a 4x4 matrix defining the determinant of a 3 by 3 matrix. Okay, we now found up to this point, this argument so far has concluded that the determinant of that 4 by 4 matrix is equal to the determinant of this 3 by 3 matrix. Okay, now we want to find the determinant of a 3 by 3 matrix. So let's again remind ourselves of the checkerboard pattern, but this time for a 3 by 3 matrix. So you alternate plus and minus signs. And so when you alternate plus and minus signs, you get this pattern of pluses and minuses. Okay, and then, so now, well, there's 2 zeros in the second column, right? So let's make our life easier again, and let's choose the second column again. So we're going to choose the second column to find the determinant of this 3 by 3 matrix. And so when we do that, now the entries we want to look at are these entries in the second column of a 3 by 3 matrix, which is checkerboard pattern. Right? Now, the top, this is going to be negative here because it corresponds to the negative sign in this checkerboard pattern. So now this is equal to, so we're going to take the negative of the first entry. It's the negative of this entry times the determinant of the corresponding submatrix. Then I would suggest you do it in the same method. You first put the entries in, and then you think about and you can put the determinant symbol in, and then you fill in what the matrix you should go. So here now it's a negative of that term. Now it's a positive of this term. It's the same. So it's going to be plus -2 times the determinant. So even though this term has a plus sign, the actual number is going to be a negative because the original number is -2. And so by the plus just means we're keeping -2 the same, not negating it. And so it's negative plus, and then this term is minus. So now we're going to take minus this entry times a corresponding determinant of a corresponding submatrix. This first thing is going to be 0 because it's 0 times something. This term is also going to be 0 because it's 0 times something. So all we care about is this submatrix because that's the only thing that will affect the value of this expression. So now if you take this entry, because this is the submatrix corresponding to this entry, you take this entry and move the row and column it's in. First, the green entries go because it's in the same column. And then the entries in the second row are also in the same row as this entry. And so you're removing these red entries also. So you remove the green and red entries. The submatrix you have is 1, -1, 2, 1. Okay? This is the submatrix you get from this one by removing the green and red entries. The first row is 1, then -1. Then the next row is 2, 1. You just leap over the green entries if it's not there. And so now this expression is equal to -2 times the determinant of that matrix because the other 2 entries are 0. And that expression is equal to -2 times the determinant of that matrix, which is 1 minus -2. Okay, so it's -2 times the determinant of this matrix, which is AD minus BC. So it's 1 times 1, which is 1, minus -1 times 2, which is -2. So it's 1 minus -2. And so then that's equal to -2 times 1 minus -2, which is 3. And so this equals -6. And so the final answer is that the determinant of this matrix is equal to -6. All right? And so notice how it required some work, but not a huge amount of work, right? If you didn't apply a shortcut here, then finding this determinant without this method could have been a very laborious task. Okay? And so the answer is -6 for the determinant of this 4 by 4 matrix. So just because the matrix is very big does not mean that it will take a really long time to compute its determinant, as long as you do it in an easier way. So example 6, we're now going to look at the determinant of an upper triangular matrix. So let's look at the determinant of an upper triangular matrix. And so here I'm going to look at the determinant of a 4 by 4 upper triangular matrix. Remember, an upper triangular matrix is one where all the entries above the main diagonal. I'm sorry, a lower triangular matrix, one in which all the entries above the main diagonal are 0. This is A11, A22, A33, A44. Those are the entries on the main diagonal. So all the entries above it in this example are 0. And so since all the entries above it are 0, the determinant becomes very easy to compute. These are the other entries. Okay, so we want the determinant of that upper triangular matrix. I mean, lower triangular matrix. Okay, so what happens is, let's take the cofactor expansion along the first row. You take the cofactor expansion along the first row, well, the only term that matters is the first term, and then you multiply it by its corresponding determinant of the corresponding submatrix, and you get this. Okay, so all I did was I took the cofactor expansion along the first row, and that means it's A11 times the determinant of this submatrix. All the other terms would be 0. And so now the determinant of this 4x4 upper triangular matrix is equal to A11 times the determinant of this submatrix, which is still the determinant of a lower triangular matrix. And if you take the determinant of that, you already have A11. If you take the cofactor expansion along the first row, again, only the first term matters, and it's A22 times the determinant of its corresponding submatrix, which is the determinant of a 2x2 matrix, which is A33, 0, A43, A44. It's just, if you remove the row and column this entry is in, you're left with this submatrix, and it's the determinant of it. And now if you take the determinant of that 2x2 matrix, then what you get is A33 times A44 minus 0. So this is A33 times A44, and it's A33444 minus 0 times that, so you get this product. And so now we found that the determinant of an upper triangular matrix is just the product of the entries on its main diagonal. It's A11 times A22 times A33 times A44. So this is a shortcut for finding determinants of a lower triangular matrix. And so the same is true for an upper triangular matrix. If the zeros were below the main diagonal, then the determinant of the matrix would still be the product of the entries on the main diagonal. Okay, so more examples. So that pattern applies to not only lower triangular matrices, but also upper triangular matrices, in which it's the determinant is the product of the entries on its main diagonal. So the so first I'm going to just say the theorem, and then I'll do another example. So example 2.12, theorem 2.12, theorem 2.1.2. If A is an n by n triangular matrix, upper triangular, lower triangular, or diagonal matrix is also a triangular matrix, then the determinants of that matrix, A, is the product of the entries on the main diagonal of the matrix. that is the determinant of that matrix A is equal to A11, A22, A33 times dot 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 times A and N. Is it the n by n matrix? So it would stop at A and N. Okay, and so that's what this was illustrating for a 4x4 triangular matrix. So it's true for any n by n triangular matrix. Okay, so if you had the determinant of a matrix 1, 0, 0, -2, 7, 0, 437, 1, 10,032, 5, and you want to find a determinant of this matrix, because it's a triangular matrix, it's a lower triangular matrix, then its determinant is equal to the product of its entries on the main diagonal. And so the determinant of this matrix is 1 times 7 times 5, which is 35. Okay, so even though there's an entry with 10,032 and another entry with 437 and -2, none of these entries matter because its determinant is determined by the product of the entries on its main diagonal. Right? So it's a very good, it's good to know that shortcut. Okay, so on the whiteboard, I'm putting up visual aids to help compute 2 by 2 and 3 by 3 to compute determinants 2 by 2 and 3 by 3 matrices. Okay, so let's do that. Okay, so these are patterns for finding determinants of 2 by 2 and 3 by 3 matrices. Myself room. So we already have the formula for determinants of 2 by 2 matrices. And I showed you this illustration already too, but I'm going to do it again. So you have A11, you have A12, you have A21, and you have A22. Right? These are the entries of your 2 by 2 matrix. To find its determinant, you just go down right and then subtract that product. So you take A11 times A22 minus A12 times A21. And so this is illustrating how the determinant of that matrix is equal to A11, A22 minus A12, A21. Okay, because the arrow going right is a positive product, is the same as the product, and the arrow going down left is the negative of that product. So when the arrows are going right down, it's the same as the product. When it's going down left, it's the negative product. Okay, so that's for 2 by 2 matrices. For 3 by 3 matrices, so I'm going to draw a green line. And so now I'm going to be talking about determinant of a 3 by 3 matrix. So there's also a visual aid to finding determinant of a 3 by 3 matrix. So it's a little bit more complicated, but it's not that hard. So let's say you start with a 3 by 3 matrix, A11, A12, A13, A21, A22, A23, A31, A32, and A33. And you want to find the determinant of that matrix. So here's going to be the pattern. So first I'm going to this has nothing to do with the matrix itself. These are just side notes. So don't think in any way I'm influencing the effect of this matrix. I'm just drawing these in for a personal, to help with the calculation. So what I'm doing is I'm repeating the first two columns of this matrix. This is the first column. I'm going to rewrite the first column here. And I'm also going to rewrite the second column here. I'm not actually multiplying or changing anything. I'm just writing it down as a visual aid. So this is the first column rewritten. And this is the second column rewritten. And if you're dealing with numbers with actual entries instead of variables, you would just plug in those numbers, you would put those numbers here. Okay, so now you have the first two columns rewritten here. So now, in order to find the determinant of this original 3x3 matrix, you just take the sums of these products going down right. So the product of those three things, plus the product of those three things, plus the product of those three things, and then subtract the product of those three things, subtract the product of those three things, and subtract the product of those three things. So the arrows that are going down right is the positive product of those entries, and the arrows going down left is the negative of those products. That's what this formula is saying, is that the determinant of that 3x3 matrix, A11, A12, A13, A21, A22, A23, A31, A32, A33. The determinant of that matrix is now equal to, just take each of the products that are going down right. So this is going to be A11, A22, A33, product of those three entries, plus A12, A23, A31, plus the next product, A13, A21, A32. So that's the sum of those three products. The arrow's going down right. And it's going to be minus the other three products. So A13, A22, A31, minus A11, A23, A32, minus the other product, A12, A21, A33. I will often just compute a 3x3 determinant of 3x3 matrix just using cofactor expansion, but you're reminded when you have this form in front of you and think, oh, why don't I just use this? So this is very easy. You just draw this visual aid, and then it tells you how to compute the determinant in this quick. Memorizing this formula would be a lot of work. It would be annoying. You could, but you know, it's easy to make a mistake memorizing this formula. It's much easier though drawing this picture and then just looking at the arrows that you draw in. Okay, and so this formula can be verified by finding the cofactor expansion along the first row. Okay, so this formula can be verified by finding the cofactor expansion of this matrix along the first row. Okay, and so you find the cofactor expansion along the first row of the matrix, not these extra entries, just the matrix itself, the first row, you will get this expression. Okay, but you can get this expression just from this picture. Okay, so the original 2x2 matrix, the visualization is very easy. And so the 3x3 one's a little bit harder, but still not that bad. So here, the next board, I'm just going to give examples where we use those pictures to evaluate determinants. So this is example 7. Okay, so find determinants using the picture illustrations in the previous whiteboard slide. Okay, so let's say you want to find the determinant of the 2x2 matrix 3, 1, 4, -2. Well, so I'm going to rewrite the matrix again, 3, 1, 4, -2. But now I'm just going to add in the arrows. Okay, so I'm just going to add in the arrows, this arrow and this one. And so what that the illustration tells you is that this is equal to 3 times -2 minus 1 times 4. And so this is equal to -6 minus 4, which is -10. Right, and so simple. Now the next one is determinant of a 3x3 matrix. The determinant of the matrix 1, 2, 3, -4, 5, 6, 7, -8, 9. And so to find the determinant of this matrix, I'm just going to rewrite the matrix again. So determinant of 1, 2, 3, -4, 5, 6, 7, -8, 9. Okay, and then I'm going to add in, these are not actually here, they're like ghosts, they're not there, they're just 1, 2, -4, 5, 7, -8. Okay, so these numbers are not really here, and I'm just using it for the visual aid to find the determinant. So now take the arrows going down right like this, and then draw the arrows in the other direction going down left. Now, how do I know to start the arrows here? It's the first down left arrow that fits. If I tried to move this up, I would only have 2 numbers in the diagonal. It's the first diagonal where there's 3 numbers in the product. So that's how I know how to start this pattern. Okay, just start as soon as you can where there's 3 numbers. And so now you just multiply those, the ones that go right, down right, or I'm going to call it right, they're all going down. So I'm going to say right or left. The ones that are going right, take the positive of those products, and the ones that are going left, you take the negative of those products. So the determinant of that original 3x3 matrix is equal to 1 times 5 times 9 plus 2 times 6 times 7 plus 3 times -4 times -8. Okay, and then it's going to be minus each of the products for the arrows going left. So it's -3 times 5 times 7 minus 1 times 6 times -8. And then minus the third product, 2 times -4. -4, that's a -4 there. And 2 times -4 times 9. Remember, not all these numbers in the original determinant, we have these phantom numbers that are not really there, and we're using those numbers for our visual aid, right? So now you just compute each of these products and you add and subtract them. And so now this is equal to, the first product is 45, 9 times 5 times 1 is 45. The next one is 12 times 7, which is 84. It's plus 84. This is 3 times -4 times -8. This is -12 times -8, which is 12 times 8, which is 96. Yep, 96. And then 3 times 5 times 7, that's 15 times 7, that's 105. That's minus 105. Then 1 times 6 times -8, there's a negative sign here, so it becomes positive, so it's a positive 48. And then -2 times -4 is positive, so this is positive. 8 times 9 is 72, so it's plus 72. So when you add up all these numbers, see, you want to choose, but you don't want to add 45 plus 84. First, you could do 96 plus 84, that's 180. So these two numbers, when you add them up, are 180. Okay, so 180. Or not, 180 plus 45 is 225. 225 minus 105 is the screen. 225 minus 105 is 120. 120 plus 48 is 168. 168 minus 72 is 96. Wait, what? 45 plus 84 plus 96 minus 105 plus 40. That's good. Okay. You have 200, 180, 225. I'll just do it between stuff. It's 225 minus 105 plus 48 plus 72. 120, 15, 240. Okay, that's 240. That equals 240. It's a 0. Okay, 48 plus 72 is 120. 120 minus 105 is 15. 15 plus 225 is 240. Okay, so the determinant of that 3x3 matrix is 240. You could do it without a calculator because you just take the sums and differences of products. All right, and so that's the end of that section. So the next section is section 2.2. 2.2, which we're going to do in the next page. 2.2 is on evaluating determinants by row reduction. Okay, so this is theorem 2.2.1. Let capital A be a square matrix. If capital A has a row of zeros or a column of zeros, then the determinant of that matrix is equal to 0. Okay, so let A be a square matrix. If A has a row of zeros or a column of zeros, the determinant of that matrix A is equal to 0. Okay, so the proof of that is just that the determinant of this matrix, capital A, can be determined by the cofactor expansion along the row or column of zeros. Okay, just choose the row or column of all zeros. The cofactor expansion of a row or column of all zeros is 0. Okay, because every entry is 0. So when you take the corresponding cofactor, the determinant of the submatrix for that entry, it's 0 times the determinant of a submatrix, and so everything becomes 0. And so the cofactor expansion is 0. And so that means the determinant of A is equal to the cofactor expansion along a row or column of all zeros, which equals 0. So the determinant of that matrix is 0. Right? Theorem 2.2.2. Let A be a square matrix. Then the determinant of A is equal to the determinant of A transpose. Okay, so the proof of this, consider the cofactor expansion along the first row of A. Okay. Now look at A transpose. Okay. The first column of A transpose is the first row of A. So take the cofactor expansion along the first column of A transpose, and it is not only the derivative, the determinant of A transpose, it is also the determinant of A. So you can think of the determinant of A as being the cofactor expansion along the first row of A. The first column of A transpose is the same as the first row of A. Oh, let me just say something. So consider the cofactor expansion along the first row of A. Now look at A transpose. The first column of A transpose is the first row of A. Also, the cofactor expansion along the first column of A transpose is equal to the cofactor expansion along the first row of A. Because since you're alternating all the rows and columns, it works out that the cofactor expansion along the first column of A transpose is exactly the same as the cofactor expansion along the first row of A. So also the cofactor expansion along the first column of A transpose is equal to the cofactor expansion along the first row of A. That means that the determinant of A is equal to the determinant of A transpose. Okay, because they both equal the same expression. Okay, so reminder that A transpose is the matrix you get when you switch the rows and columns of A. Okay, so the first row of A transpose is the first column of A. The second row of A transpose is the second column of A. You switch the rows and columns and you get the matrices. You get the matrices transpose. Sorry. Okay, so we have that the determinant of A is equal to the determinant of its transpose. So these are examples. I'm going to do this on the whiteboard. Okay, so on the whiteboard are examples of how elementary row operations change the value of the determinant of matrix. Okay, so we're going to take a matrix and then we're going to do an elementary row operation on it. And we're going to see how it affects the determinant of the matrix. So if you start with a matrix here, where the first row has k is multiples of k. So ka11, ka12, ka13. So only the first row is going to be multiplied by k. All the other entries are the same as what they originally were. Okay, so all the other entries are exactly the same, and only the first row is being multiplied by k. Okay, so then the relationship between the terms of that matrix and the determinant of the ones without any k's is it's equal to k times a11, a12, a13, a21, a22, a23, a31, a32, a33. Okay, so what's happening here is that you can look at it in two perspectives. You could look at it from right to left or left to right. It's saying the determinant of B, where B is the left matrix, is equal to K times the determinant of A, where A is the right matrix. Okay, so B is just the matrix you get by multiplying the first row of A by K. B matrix B is the matrix you get by multiplying the first row of matrix A by K. Okay, so this matrix here on the left is the matrix you get by multiplying the first row of A by K. And the determinant of B is equal to K times the determinant of A. Okay, and so the elementary row operation here is multiplying a row by a non-zero constant. Okay, so our elementary row operation is multiplying a row of a matrix by a non-zero scalar. Okay, so by multiplying a matrix A, a row of matrix A by a non-zero constant K, result is a matrix whose determinant is K times the determinant of the original matrix. Okay, so this is one elementary row operation, multiplying a row of a matrix by non-zero scalar, and there is a relationship between the new determinant of the new matrix and the determinant of the old matrix, before and after that elementary row operation. Okay, to help you understand this, matrix B is the matrix that is the matrix after the elementary row operation. Matrix A is the matrix before the elementary row operation. Okay, so the matrix on the right is the matrix before the elementary row operation, and matrix B is the matrix after the elementary row operation. On this slide, the elementary row operation is multiplying a row of a matrix by non-zero scalar. We only multiplied one row by that scalar, not the entire matrix. Okay, so another thing that can happen with an elementary row operation is that let's say you start with a matrix A11, A12, A13, A21, A22, A23, A31, A32, A33. Okay, so you have that matrix there. Now on the left side, there's going to be something else I'm going to write. So what I'm going to do is the elementary row operation is going to be the first and second rows are going to be interchanged. So this is the first row, and this is the second row of our original matrix. This is before the elementary row operation. Afterwards, we're going to get another matrix. And so I'm going to put here in text what I'm doing here. So the elementary row operation. The elementary row operation is switching rows 1 and 2. Okay, and so now the matrix on the left is going to be after you switch rows 1 and 2. So row 1 is going to become row 2. Now it's A11, A12, A13. The indices are representing where the entries were in the original matrix. And so now the indices for this matrix will not denote where they are in the matrix. And so now the second row is becoming the first row. This is A21, A22, A23. We just switched the first and second row of the original matrix to get these two rows. Okay, this row went here, and this row went here. We just switched them. And now the third row is unaffected. So the third row stays A31, A32, A33. But what we're doing here is we're describing the relationship between the determinant of the old matrix before we switch the rows and the determinant of the matrix after we switch those two rows. So the determinant of the new matrix is equal to the negative of the determinant of the old matrix. Okay, so the determinant of a matrix after you switch two rows is equal to the negative of the determinant before you switch the two rows. Okay, so this is an example of how the determinant of a matrix B, which is the matrix after the elementary row operation of switching rows 1 and 2, is equal to the negative of the determinant of A, which is the original matrix before you switched rows 1 and 2. Okay, so the determinant of B is equal to negative determinant of A. And matrix B, matrix B is the matrix that results, that is the matrix after the elementary row operation of switching rows 1 and 2. And matrix A is the matrix before the elementary row operation of switching rows 1 and 2. So our equation here is relating the determinants before and after this elementary row operation. Okay, so this is an example of there are three classes of elementary row operations we talked about. Multiplying a row by non-zero constant. That was this. So this is an example of multiplying a row by non-zero constant. In this case, row 1. Even though we chose an arbitrary constant, we chose row 1. We could have chosen row 2 or row 3, and we could have chosen a different size matrix. This is one example of that type of elementary row operation. This is one example of this type of elementary row operation, which is switching two rows. We're not switching two columns, we're switching two rows. Okay, so here we're talking about switching two rows. Anytime you're switching two rows, the determinants are the same. And this is an elementary row operation. Okay, and then so the third one is the hardest one. So we have to make things more difficult. So we're going to start All right, I'm gonna have to give myself a lot of room. So on the right side is going to be the determinant of our original matrix. We're gonna have our original matrix, A11, A12, A13, A21, A22, A23, and A31, A32, and A33. So if you're having trouble understanding this part, I would understand the first two before I understand this one. I mean, when you look back, try to get it now. Okay, so this is your old matrix. And so this is before the elementary operation. The elementary operation we're going to do is we're going to add a constant multiple of one row to another row. Okay, so what we're going to do is we're going to add a constant multiple of row 2 to row 1. So I'm going to type that here. So the elementary row operation is adding a constant multiple of row 2 to row 1. So we're going to add a constant multiple of row 2 to row 1. And we're going to look at the effect, the relationship between the determinant of the resulting matrix after this elementary row operation and the determinant of the matrix before we did it. Okay. So first, what is the matrix you get by adding a constant multiple of row 2 to row 1? Well, the effect of this is to change row 1. After 2, the row after the word 2 is the row affected by this elementary operation. So the only row that's affected is row 1. So rows 2 and row 3 stay the same. So that means that I'm going to rewrite rows 2 and 3. It's always good to start with the easiest thing. Usually good to start with the easiest thing and then worry about isolate the problem. So this is A31, A32, A33. So the problem is what happens with row 1, right? So this elementary row operation only changes row 1. Okay, so I rewrote rows 2 and 3. So what happens? You're adding a constant multiple of row 2 to row 1. So originally, the first entry in row 1 was A11. But we're adding a constant multiple of row 2. So this is A11 plus K A21. It's a constant multiple of the first entry in the second row added to the first entry in the first row. And this is A22. The next entry is A22. Next entry is A12, which is this original entry here, A12, and we're adding a constant multiple K to the corresponding second entry in row 2, which is A22. So it's A12 plus K A22. And then the original entry in row 1 here was A13, where we're adding a constant multiple of the corresponding entry in row 2, which is plus K A23. So now our first row looks like this. This is the resulting matrix of adding a constant multiple of row 2 to row 1. The determinant of that resulting matrix is the same, it's equal to the determinant of the original matrix. And so when we add a constant multiple of one row to another, we do not change the determinant of the matrix. That's what that's illustrating. Okay, so this is, okay, so if the resulting matrix is matrix B, and the original matrix is matrix A, then this relationship is that the determinant of B is equal to the determinant of A. Okay, and so matrix B is the matrix that results from adding a constant multiple of row 2 to row 1. Okay, and then matrix A is the matrix before adding a constant multiple of row 2 to row 1. Okay, so that results or after. Okay, it's the matrix after adding a constant multiple row 2 to the row 1. So B is what happens, is the matrix after you add a constant multiple row 2 to row 1, and matrix A is the matrix before adding a constant multiple of row 2 to row 1. So determinant of B is equal to determinant of A. So adding a constant multiple of one row to another does not change the determinant of the matrix. That's what this illustrates. Okay, so these three illustrations are illustrating this next theorem I'm going to write down. Before I do that, I'm just going to quickly show this again. I spent a lot of time on it. So then we have this relationship, right? Multiplying a row of matrix by non-zero scalar. We switch rows 1 and 2 here, right? Okay, so then I didn't do the pink thing here. So I don't want to. Okay, so that I think it's better without there. Okay, so that's good. Okay, so now those three slides illustrate this next, or examples of this next theorem. Okay, so those examples illustrate this next theorem. Okay, so this is theorem 2.2.3. Let capital A be an n by n matrix. Part A. If capital B is the matrix that results when a single row of column, where a single row or column of A is multiplied by a scalar k, then the determinant of B is equal to k times the determinant of A. So on the other slide, as I was focusing on elementary row operations, right? But you could also multiply a column of a matrix by a scalar k and get this relationship also. So it works for rows or columns. But keep in mind that multiplying a column by a non-zero constant is not an elementary row operation. Okay, only multiplying a row by non-zero constant is an elementary row operation. And so the row might be more useful, but the column actually, there are some times where that also is useful. Okay, so part B, if B is the matrix that results when two rows or two columns, okay, so rows and columns don't matter for this theorem. When two rows or two columns of A, are interchanged or switched, then the determinant of B, the resulting matrix, is equal to the negative of the determinant of the original matrix A. And then part C is that if B is the matrix that results when a multiple of one row is added, when a multiple of one row of A is added to another row of A, or when a multiple of one column of A is added to another column of A, then the determinant of B is equal to the determinant of A. Okay, so this also works for columns. I gave you an example illustrating a row, but you could do the same thing with a column, add a constant multiple of one column to another. The determinant of the resulting matrix is equal to the determinant of the original matrix before you did that column operation. Okay, and so this is just a general statement that includes the examples that were on the whiteboard. It says theorem 2.2.3. So the next theorem, 2.2.4, is specific to elementary matrices. So let E be an n by n elementary matrix. Remember, an elementary matrix is one that results by doing exactly one elementary row operation on an identity matrix, right? So a reminder, an elementary matrix is a matrix that results from doing exactly one elementary row operation on an identity matrix. Okay, so there's lots of elementary row operations and there's lots of identity matrices because each size square matrix has its own identity matrix. There's an identity matrix for a 1x1 square matrix. There's an identity matrix for a 2x2 square matrix. There's an identity matrix for a 3x3 and so forth. And so each of them, if you do only one single elementary row operation on any of them, that results in an elementary. They all result in elementary matrices. So there's lots of them. So, but let A be any n by n elementary matrix. Part A. If E results from multiplying a row of an n by n identity matrix, which is I sub n, by a non-zero constant, by non-zero number k, then the determinants of E is equal to k. Okay, so if you have an elementary matrix that you got by multiplying a row of an identity matrix by non-zero number k, the determinant of that resulting elementary matrix is equal to k. If E results from interchanging two rows of an n by n identity matrix, then the determinant of that resulting elementary matrix is equal to -1. Okay, so if you take an identity matrix and you interchange two rows of it to get an elementary matrix, the determinant of that resulting elementary matrix is -1. Okay, this can be derived from our previous theorem because it said that the relationship between when you switch two rows of a matrix, it could be also be two columns, but here specifically it's two rows. It has to be two rows here. When you switch two rows of a matrix, the relationship between the determinant of the new matrix and the old one is that they're negatives of each other. And so the determinant of an identity matrix is 1. And so if you switch two rows in an identity matrix, the resulting determinant has to be the negative of the determinant of the original matrix. And since the original one is always 1, the determinant of any identity matrix is 1, the determinant of the resulting elementary matrix from switching two rows has to be -1, the negative of 1, which is negative. So this comes directly from the previous theorem. C, if E results from adding a multiple of one row of in to another, then the determinant of that elementary matrix is equal to 1, because in the previous theorem, it said that if you add a multiple of one row of a matrix to another one, it doesn't change the determinant. The determinant stays the same. The determinant of the new matrix is equal to the determinant of the old one. And so if you take an identity matrix, which has determinant 1, and you add a constant multiple of any row of an identity matrix to another row of that identity matrix, then the new matrix is an elementary matrix that you got from doing that, but its determinant is the same as the determinant of the old identity matrix, which is 1. So the determinants of all elementary matrices attained that way, all of them, their determinants are 1. Okay, and so this theorem is directly from the previous theorem, the relationships of matrices before and after an elementary matrix, before and after an elementary row operation. Okay, so let's do examples. Okay, so this is example 1. So if you take the determinant this 3 by 3 matrix, where it's 1, 0, 0, 0, 3, 0, 0, 0, 1. Well, we know as a triangular matrix. Is that okay? Is that enough? Okay, that's the last line is there, right? Okay, so if we want to determine this, we know as a triangular matrix, a diagonal matrix is a triangular matrix. This determinant is the product of the entries on its main diagonal. So the determinant of that matrix is 3. But this is also 3 times you multiply the second row of I sub 3 by 3. And so you also know this is equal to 3 times the determinant of I sub 3, which is 1. So this is 3 times 1, which is 3. So we have the determinant of this matrix because it's an elementary matrix. Okay, the above matrix is an elementary matrix obtained by multiplying the second row of I sub 3 by 3. That means that its determinant is 3. Okay, by part A of this last theorem, which was theorem 2.2.4. Okay, so by part A of theorem 2.2.4, it says if let E be an elementary n by n matrix, an n by n elementary matrix. If E results from multiplying a row of In by non-zero number k, then the determinant of E is equal to k. So here, this matrix is an elementary matrix, so it's a matrix E in that theorem, and it's attained by multiplying the second row of I sub 3 by 3. So that means its determinant must be 3, equal to 3. Okay. Okay, so theorem 2.2.5. If A is a square matrix with 2 proportional rows or 2 proportional columns, then the determinant of A is equal to 0. Okay, so what does proportional mean? It means that the ratios of the corresponding values are the same. So example, if you have a matrix, so let's take the, okay, so we have a 3 by 3 matrix here. And so let's say you want to find a determinant. Oh, okay. So you want to find a determinant of this matrix. Okay. Well, the first and second column in this matrix are proportional. The first and second column of the above matrix are proportional. So by theorem 2.2.5, that means that its determinant is 0. Okay, now how could you see that without theorem 2.2.5? Well, without theorem 2.2.5, we can observe that, so it's basically the reason for the proof, kind of, but just applied to this matrix. If you take the determinant of this matrix, well, we know that the relationship between, in this theorem, it said that if theorem 2.2.3, it says if B is the matrix that results when a multiple of one row of A is added to another row of A, or or when a multiple of one column of A is added to another column of A, then the determinants are the same. So I can add a multiple of one column to another, and the determinant is the same. So the determinant of that matrix is equal to the determinant of the matrix I get by adding -2 times the first column to the second column. So I'm going to take -2 times the first column and add to the second one. Because they're in proportion, that means that there exists a constant in which I could multiply one row or column by, add it to another row or column, and get all zeros. And so that means that, so for instance, in this case, columns 1 and 2 are in proportion because the entries in column 2 are twice the corresponding entries in column 1. That means if I take the entries in column 1, multiply each of them by -2 and add them to column 2, I get zeros in column 2. I added -2 times the first column to the second. And the result is that the determinant of the new matrix is equal to the determinant of the old one. And so now the determinant of this matrix is equal to the determinant of this one, but this one has a column of all zeros, which means that by our previous theorem, it's equal to 0. The determinant of any matrix, which there's a row or column of all zeros, is equal to 0. So that means the determinant of this matrix is 0. And so we found that without theorem 2.2.5. But we then needed theorem 2.2.3, which drew this conclusion, part C. And then we also used this previous theorem that said the determinant of a matrix with a row or column of all zeros is 0. Determinant of a matrix. Here, this theorem 2.2.1. Let A be a square matrix. If A has a row of zeros or column of zeros, then the determinant of that matrix is 0. And so we use that right here. This is a matrix who has a column of all zeros, and so its determinant is 0. You could have also found the cofactor expansion of this matrix along the second column and got it to be 0, which means its determinant is 0. Okay, so we found in 2 ways that the determinant of this matrix is 0, both using theorem 2.2.5 directly or using 2 other theorems earlier. Okay. Another example is example 3. So we use row reduction to find the determinant of the following matrix. Okay, so we're going to use row reduction to find the determinant of the matrix. So here's our matrix. So we want to find the determinant of. And so it's a 3x3 matrix. And so it wouldn't be ridiculous to find its derivative to find its determinant directly, but we can sometimes make things easier on ourselves with different methods. So here we're going to use row reduction to find its determinant faster. Okay, so first I'm going to switch the first and second rows of this matrix. And so when I switch the first and second rows, the determinant of the new matrix, the relationships are that the determinants are negatives of each other. So you get 3, -6, 5, 3, -6, 9, 0, 1, 5. So I switch the first 2 rows, and that means that the third row stays the same, but their determinants are negatives of each other. Okay, then what I'm going to do is I'm going to factor out the 3 from the first row. So and so that means that I already have a negative sign because there was a negative there, but now I can put a 3 here because what I'm going to do is I'm going to relate that with the derivative of the matrix in which the entries in the first row are 1/3 of the original ones. So now you have 2, 6, 1. So remember, if the effect of taking a matrix, multiplying one of its rows by 3, is that its determinant is 3 times the determinant of the original matrix. So the determinant of this matrix is 3 times the determinant of that one, and there's a negative sign in front. So it's the negative of the determinant of this one, which means it's a negative of 3 times the determinant of that matrix. Okay. And so now what I'm going to do is I'm going to take a constant multiple of the first row and add it to the third row. So I have a -3 from before, the negative times the 3. So I just shortened it to -3. And now here, the second row is unchanged by this operation. What I'm going to do is I'm going to take -2 times the first row and add it to the third row. And so if I do that, then what I'm changing is only the third row. So I'm taking -2 times the first row and adding it to the third one. So if you do that, -2 times the first row and add to the third, you get these values here. Okay. Now, the effect of adding a constant multiple of one row to another is that the determinants are the same. It doesn't change it. So that means the result, the effect of adding -2 times the first row to the third does not change the determinant. So I can say these two are equal. I didn't change anything here. These two are just equal. Even though the matrix is different, the way I changed the matrix did not change its determinant. Okay, and then this is equal to, so I still have a -3 here. But now, so okay, let's go. So then, so now what I can do is I can continue row reducing this. And so what I want to do now is I want to get this matrix to a triangular matrix. You notice that the only thing stopping this matrix from being triangular is that there's a 10 here. If I can get rid of this 10, make this a 0 in such a way that everything is 0 is below the main diagonal, the determinant that we'll have is a determinant of a triangular matrix, which means it's the product of the main diagonal terms. So I just need to add -10 times the second row to the third one to get rid of this 10. So I'm going to do that. And so remember, adding a constant multiple, a non-zero multiple of one row to another does not change the determinant. The determinant of the new matrix is going to be equal to the determinant of the old one because of the operation we chose. So the second row stays the same, 0, 1, 5. And I'm going to take -10 times that row and add it to this one, which means that this is a 0, that's a 0. I chose -10 because -10 times 1 is -10, and then -10 plus 10 is 0. So -10 times 1 plus 10 is 0. -10 times 5 is -50. -50 plus -5 is -55. So now you get that. The effect, again, does not change the determinant. So the determinant of the new matrix is equal to the determinant of the old one. But now this is an upper triangular matrix, which means that its determinant is equal to the product of the entries on its main diagonal. And so this is equal to -3 times the product of the entries on its main diagonal. And so I'm going to put in a bracket just so that you can see the difference between where these numbers come from. So this is the determinant of that matrix. This is 1 times 1 times -55. Okay, so it's -3 times the determinant of that matrix, which is 1 times 1 times -55. If you multiply all those numbers, you get 165. Okay, because multiplying by 1 doesn't change the product, but then -3 times -55 is positive, 3 times 55. 50 times 3 is 150, 5 times 3 is 15, 150 plus 15 is 165. So 3 times 55 is 160. So then that's 165. And so that's the determinant of the original matrix. Okay. Okay, and so now one more example. I guess we have time for another example. That example is, let's do example 4. And so, so we have a 4x4 matrix. I'm going to assign homework too, so don't run out of here. Right? Give me I'm going to need a second to assign homework after this lesson. So we have 1, 0, 0, 3. We have 2, 7, 0, 6. 0, 6, 3, 0. And then 7, 3, 1, -5. Good. Okay, so now, so we have this matrix, and so what we have to do is just make this into a lower triangular matrix, right? There's this 6 here, and this 3 here are not good because they prevent it from being a lower triangular matrix. And so we just fix it by getting rid of them by elementary row operations. And then by doing that, we can find the determinant after we get rid of them using elementary row operations. So we're going to add constant multiples of oh, okay, sorry. Okay, so we want to get rid of 3 and 6. So it's a little tricky. So you take the first column, -3 times it, add to the last column, and it gets rid of it. Okay, so 1, 2, 0, 7. 0, 7, 6, 3, 0, 0, 3, 1. And we're going to add -3 times the first column to the third. And then what we'll get is 0, 0, 0. But -3 times 7 is -21. -21 plus -5 is -26. And so this is, so that was from, so we added -3 times the first column to the fourth column. That did not change the determinant of the matrix. Okay, so the determinant of the new matrix equals the determinant of the old one because of the operation we chose. And now this is a lower triangular matrix, which means its determinant is equal to the product of its derivatives. Okay, so we're just going to multiply all the entries on its main diagonal. 1 times 7 times 3 times -26. And when you multiply those numbers, you get 21 times -26. And that's equal to -546. Okay. And so that's the determinant of that matrix. Okay, so if you use the best method, it goes a lot faster. Okay, so we're up to 2.3. So the exam is on chapters 1 and 2, up to including 2.3. So we're pretty close to done with the material. So I'm going to announce the day of the next exam. Okay, so the next exam is going to be, we're going to finish the material and you're going to have some time to study for the exam. So I'm actually going to announce the exam with a little extra time. I'm going to make it November 9th. Okay, so the exam is going to be November 9th. Okay, so test 1 is on November 9th. Okay, during class on Zoom. Okay, that's a little over 2 weeks from today. Okay, so you have a little more than 2 weeks for the exam. Okay, the second exam, there will not be a huge gap between the first and second exams. Okay, but the first exam is going to be on November 9th during class. Okay, so test 1 is on November 9th during class on Zoom. Also assigning homework. Okay, so so the homework for today, so the homework is going to be so give me a minute. Okay, so next is the homework is going to be the section for 1.8, 1.9. So let me go to the homework here. Okay, so the homework so the problems from 1.8. So let me share the so the problems from 1.8 there's one problem of 1.9. And I'm also citing problems from 2.1 and 2.2. Okay, so all of that, it's due on Tuesday. Okay, so it's a lot of homework over the weekend. Okay, and so we'll go over that next class. There's only one more section on the next exam, and it's a little over 2 weeks. Okay, so you have plenty of time to study all these things, but I want you to do a lot of homework over the weekend. Okay, the review sheet. So this is the homework / review sheet. I also made a practice exam for you, so that's like your review sheet. So you can take the practice exam to prepare for the exam, and it's easier this way. These are the problems I want you to know for the exam. Okay, they're also the homework problems, and the review, the practice test is your practice for the exam. Okay, so we have these 4 sections. I want you to do the exercise set from this sheet. This is from the review sheet for test 1. This is 1.8, 1.9, 2.1, and 2.2. Okay, so that's what I want you to do. 1.8, 1.9, 2.1, 2.2. Okay, so 1.8, 1.9, 2.1, 2.2. Okay, and so this is due next class on Tuesday, November 26th. Okay, Tuesday, November 26th, 2021. Okay, right, any questions about the homework or the test? Oh, also, test 1 is on November 9th during class on Zoom, and the review for test 1 will be the class before, and that will be the review for test 1 will be on November 4th. Okay, November 4th during class on Zoom. Okay, everything's on Zoom using the same link that we always use. So you'll be using the same link to get to this lesson as you will for the exam. No, not October, not October, not October. Don't listen. It's October now. Oh, for the homework. Yes, October 26th. Thank you. Okay, so it's due October 26th, 2000. Due next class on Tuesday, October 26th. Okay, and then test 1 is November 9th, and review for test 1 is November 4th. Okay, good. Okay, I think that covers everything. So there'll be plenty of time for the exam. Okay, so have a good night, and I'll see you on Thursday. You too. Good night, everyone. Thank you for being here.